Yes, good morning, students. So today we are going to discuss the topic P block elements. Can you see the screen? Yes, thank you. So we'll start with the topic P block elements. Okay. So what are P block elements? Where do you find P block elements in the periodic table? Yes, P block elements are present in the center. Okay. They are towards the right side, right? They are towards the right side. So which are the P block elements? They are from 13. So right, 13, 14, 15, 16, 17, 18, right? So these are the six groups. So these are the six groups of P block elements in the periodic tables, that is from group 13 to group 18. So these comprise of P block elements. So why it is said to be P block element? Why it is said to be P block elements? Because the last electron enters the what? It enters the outermost P orbitals. Okay. So you know in P, so P orbitals, it consists of how many? There are three orbitals, right? So they consist of three orbitals. So maximum how many number of electrons it can accommodate? It can accommodate six. It can accommodate six. So P orbital, it consists of three orbitals. So P orbitals totally it can maximum number of electrons which can accommodate is 6. Okay, so which are the elements from group 13 to group 18? They comprise of P block elements. So these consist of what? They consist of non-metals and metalloids. Okay, they consist of non-metals and metalloids. These are only existing in P block elements. So what happens to non-metallic character as you go down the group? Okay, the non-metallic character, it decreases. Okay, so heaviest element in each P block element is the most metallic in nature. So as you go down the group, what happens to non-metallic character? It decreases and metallic character increases. Okay, so this is about the P block element. So you can see the position of P block element. So you can see your right. So these are the P block elements. So from 13, 14, 15, 16, 17, 18. So these are the P block elements towards your right side of the periodic table. So these are the P block elements. So P block elements, so your which are the elements present? First we'll see with group 13. Okay, so with which are the elements present in group 13? It is boron, right? So first is your boron, then aluminium is there, right? So boron, aluminium, then gallium, indium, okay, thallium. So these are all elements present in your group 13. Okay, so boron is a non-metal, aluminum is a metal, okay, and gallium, indium, thallium, these are metallic in character. So as we have discussed, as you go down the group, non-metallic character, it goes on decreasing. Okay, so this is about the elements. So what is the general electronic configuration? So in general, for P block elements, it is NS1 to NS2, NP1 to NP6. Okay, this is for general electronic configuration for P block elements. For group 13, what is the electronic configuration? It is NS2, NP1. Okay, so the general electronic configuration of element is NS2 to NP1 to NS2 to NP6. So hence there are six families in the P block elements. So what happens to non-metallic character? It decreases down the group. So boron family, the outermost electronic configuration is NS2NP1. Carbon family NS2NP2. Nitrogen family NS2NP3. Oxygen family NS2NP4. Halogen family NS2NP5. And noble gases, okay, NS2NP6. So these are the electronic configuration of each group. So first comes your boron family. So first we'll discuss about the boron family, that is group 13 elements, boron family. So what is the electronic configuration? It is NS2NP1. So so what happens here? So boron and aluminum have noble gas core. Okay, so when you see the electronic configuration, boron and aluminum, it has a noble gas core, and gallium, indium has noble gas core, plus it has d electrons. Okay, and when you see thallium, when you write the electronic configuration of thallium, so thallium, it has a noble gas electrons plus 14 F or electrons, F orbital electrons, and 10d electron core. So these are the general electronic configuration. So as you write the general electronic configuration according to above principle, so these are the electronic configuration of the elements. So you can see here. Okay, so you can see here as we had discussed. Okay, so boron, aluminium, gallium, right? Indium has what? Inner core gas electron plus 10 electrons, d electrons, and thallium you can see here, F orbitals are there. 14 electrons are present in F orbitals plus your 10 electrons from the d orbitals. Okay, so this is the general electronic configuration of group 13 elements. So boron, right? So boron is a rare element. Okay, so where it is found mostly in orthoboric acid, borax. Okay, then sodium borate, kernite. So kernite, what is the composition? Na2B4O7. Okay, then in India, borax occurs in Puga Valley and Sambar Lake. Okay, so these are the occurrences where you get your borax. So the abundance of boron in Earth crust is less than 0.001% by mass. Okay, so this is the what the two isotopes of borons are 10 boron and 11 boron. Okay, so these are the occurrence of boron. So aluminium also, you know, it is the most abundant metal and it is the third most abundant element in the Earth's crust. Okay, so so this is about bauxite. Bauxite and kyrolite are the important minerals of aluminium. So remember this: bauxite, okay, Al2O3.2H2, and kyrolite, okay, Na3AlF6. So these are the important minerals of aluminium. Then in India, it is found as mica. Okay, mica, MICA. So remember the composition. Gallium, indium, and thallium are less abundant in nature. So these are the occurrence of different elements. So what happens to atomic radii? So as you go down the group, atomic radii goes on increases. Why? Because extra shell is going to as. Okay. This is because of the, so this is the variation in atomic radii. So as you go down the group, what will happen? Atomic radii increases. Why? Because there is addition of extra shells. Okay. So you can see there is one deviation is noticed, atomic radii of gallium. It is 135 picometer, and which is less than that of aluminium, 143. So aluminium, it is above. Okay, but the aluminium has a atomic radii of 143, while there is atomic radii of gallium is 135. So why is it so? Why there is sudden increase here? Okay, why there is sudden decrease here? So this is because of the variation in inner core of electronic configuration, right? So because there is d electrons, right? D electrons are in your gallium. Okay, so because of this presence of so there is inner core of electronic configuration. So this, because of the variation in inner core of electronic configuration, you can see this deviation. So the atomic radii of gallium is less than aluminium because of its poor screening effect. Okay, so this is the reason. So this, you can see aluminium. Okay, aluminium you can see here, and this is the gallium. Okay, what happens to ionization enthalpy? What do you mean by ionization enthalpy? Ionization enthalpy is the energy. Okay, it is energy which is released when you are energy required to remove a last electron from an isolated gaseous atom. Okay, so what happens? So it shows irregular trends. Okay, as you go from moving down, the ionization enthalpy decreases from boron to aluminium. Okay, and slightly gallium, there will be a higher ionization enthalpy, and then aluminium due to the poor shielding of intervening d orbital. So because of the presence of d orbital, so it is showing poor shielding effect. Okay, so it again decreases and then again increases the last element. So this is the ionization enthalpy. Okay, so electronegativity, what happens to electronegativity? You can see here electronegativity. So down the group, the electronegativity, what happens? It decreases from boron to aluminium. You can see it decreases. This is due to what? Difference in the atomic size of the element. It is due to the difference in the atomic size of the element. So this is about the electronegativity. Okay. So there is a something called as inert pair effect. Important. What is inert pair effect? The phenomena of electrons remaining paired in valence shell is called as inert pair effect. Okay. So why it is so? It is due to the reluctance of the s of electrons of the valence shell to take part in bonding. So s electrons which are inert, okay, which are present in the inert that is valence shell, they take part in bonding. So it occurs. Why it occurs? It occurs due to the poor or ineffective shielding of the ns2 electrons of the valence shell by intervening d and f electrons. So it increases down the group, and those lower elements of the group will exhibit lower oxidation state. So inert pair effect is nothing but it is due to the electrons which are remaining in the valence shell. Okay, the phenomena of electrons which are remaining in the valence shell is called as the inert pair effect. So it is why it is occurring due to the poor or ineffective shielding of the ns2 electrons. Okay, so this is inert pair effect. So oxidation state, boron, aluminium, it shows various oxidation state like +3. So boron and aluminium, it occurs in +3, while your gallium, indium, thallium, it exhibits both as +1 and +3. Okay, as we go down the group, that is of group 13, due to inert pair effect, the tendency to exhibit +3 oxidation state decreases and tendency to attain +1 oxidation state increases. Okay, so remember, boron and aluminium, it shows only +3 oxidation state, while gallium, indium, and thallium, it shows +1 and +3. So this much you have to remember in oxidation states. So what do you mean by Lewis acids? Okay, what do you mean by Lewis acid? Yes, so your boron, okay, boron is a boron trifluoride is a trivalent molecule. Why? Because boron is attached to 3 fluoride atoms, right? So it is called as, it is a trivalent molecule of boron. So the number of electrons around the central atom of boron is only 6, right? Only 6. To complete its octet, it requires 8 electrons, right? So it has a incomplete octet. So therefore, boron is said to be electron deficient molecule, and boron, it has always a tendency to accept a lone pair of electrons, right? If it accepts a lone pair of electrons, it will achieve a stable inert gas configuration. So it is acting as boron. Your boron trifluorides are acting as a Lewis acid. So what are Lewis acid? It has a tendency to accept a lone pair of electrons. So you can see the example here. So boron trifluoride is trivalent in nature. Here you can see your ammonia is there. So ammonia, it is giving its lone pair of electrons, right? So it is acting as what? It is acting as a Lewis acid, right? So it is because it is electron deficient. Boron trifluoride is electron deficient. It has incomplete octet. So lone pair of electron is given by ammonia. Thus, it is so it completes a octet, right? So it behaves as a Lewis acid. So remember this. So boron compounds, most of the boron compounds are electron deficient. Okay, they are electron deficient. So here you can see AlCl3. Okay, AlCl3, it exhibits like this. Okay, it is called as dimer. This is called as dimer. You can see AlCl3, the structure. This is dimer. What is dimer? It is a molecule or molecular complex which is consisting of 2 identical molecules which are linked together. Okay, so here this is a dimer. So always the AlCl3. Okay, AlCl3, the stability of this AlCl3 is formed due to the formation of dimer. So dimer is nothing but 2 molecules. Here you can see 2 AlCl3 molecules. They are joined. Okay, they are linked together. So it forms a dimer. Okay. So next we'll see the chemical properties. So when boron is heated with oxygen at 1000 Kelvin, so it forms boron trioxide. Okay, so it forms boron trioxide. So these are certain chemical reactions. So for next is with halogen. So when boron reacts with halogen, it forms boron trichloride. Okay. Then with the water, so what happens? So pure boron, it does not react with water. Aluminium decomposes boiling water, evolving hydrogen. Okay, so you can see boron, it does not react with water. Aluminium, the reaction is given from aluminium. So aluminium, when it reacts with water, it gives you aluminium hydroxide. Okay, aluminium hydroxide and H2, that is hydrogen gas, is liberated. So gallium and indium are not attacked by pure cold or hot water. Thallium is little more reactive than gallium and forms an oxide of the surface. Okay, so just remember that water does not react with water. Okay, boron does not react with water. Aluminum, it reacts with water to give you a aluminum hydroxide. So anomalous properties, what do you mean by anomalous property? How the first element, okay, how the first element, that is boron, is how it is different, okay, how it is different from the other elements of the group. So boron is non-metal. So as we had discussed, boron is a non-metal, okay, and while the other members of the group are metal. So anomalous behavior is nothing but how the first element is acting different, okay, how it has different properties than the other elements. So boron, it shows allotropy, okay, it shows allotropy, while other members, they do not show allotropy. Okay, allotropic forms. So you know allotropic forms. Okay, different allotropic forms. So boron, it shows different allotropic forms, but while the other members, they do not show the allotropic forms. So the elements of group 13, boron has highest melting point and boiling point, while other elements of the group, they do not have they do not have the highest melting point and boiling point. Okay, so amongst the element group, the boron, it has the highest melting point and boiling point. Then boron forms covalent compounds. Okay, why? Because the covalency of boron is 3. Okay, it can form the maximum covalency of the boron is 3, while the other members, they form both ionic as well as covalent compounds. So this is some of the properties of boron, how it is acting different from the other groups. So when you're talking about the oxides and hydroxides of boron are weakly acidic. Aluminium are amphitheric. Okay, amphitheric means what? It acts both as acid and base, while those of rest of the members are most basic. Okay, so oxides and hydroxide of boron are acidic. Aluminium is amphitheric. It acts both as acid and base, while the other members are basic in nature. Then boron hydride is quite stable, while hydrides of other members are less stable. Only boron combines with active metals such as Mg to form borides, while rest of the members do not. So Mg, so remember this reaction. So only boron, it combines with active metals, okay, to give you borides. So that is Mg plus 2b. When you heat, gives you Mg3b2, that is magnesium boride. So crystalline boron is unreactive. So when boron reacts with alkali, okay, alkali like your NaOH, right? NaOH, so it gives you borates. So sodium borate is formed here, Na3BO3 plus H2 gas is liberated. So when reaction with acid, so acid here taken is nitric acid. So boron, when it is reacted with nitric acid, it gives you H3BO3, okay, plus 3NO2, nitric oxide. So this is the reactions. So boron, where it is found? So it is found in glasses. It is used for glasses, ceramics, and agriculture. Where aluminum is used in electrical devices and construction materials. Gallium is used as for amplifiers, solar cells, and satellites. Indium coating for coatings and alloys. Thallium in photoelectric cell and toxics. Okay, so these are the applications where you can use your boron, aluminum, gallium, indium. Okay, so boron, so we'll see some of the compounds of boron now. So boron, the first compound is borax. Okay, first compound is borax. So it is the most important compound of boron. Okay, it is the most important compound of boron. It is wide crystalline solid of formula Na2B4O7.10H2O. So remember this formula of borax. Okay, so it dissolves in water to give a alkaline solution. So this is the preparation. Okay, so this is the you can see borax. Okay, borax, when you dissolve it in water, okay, it forms orthoboric acid or orthoboric acid H3BO3, okay, plus NaOH. So when you heat this borax, first loses its water molecule and swells up. On further heating, it turns into a transparent liquid which solidifies into glass-like material known as borax bid. Okay, important. So what is borax bid? Okay, so this is the reaction. So first your borax, you are heating it. So you are heating it to give you what? To give you Na2B4O7. That is, it loses its water molecule. Okay. Further heating, it gives you sodium metaborate. Okay. Sodium metaborate. That is NaBO2 plus B2O3. So this is the reaction for borax. So where this borax is used in manufacture of optical and hard glasses. It is used in enamels and paints for earthen pots. It is used as antiseptic. Okay, it is used in preparation of medicinal soaps and as food preservatives. It is used as flux. Okay, it is used in borax bead test. So remember this. Next is orthoboric acid. Orthoboric acid is H3PO3. Okay, what is orthoboric acid? It is a white crystalline solid with soapy touch. It has a soapy touch. It is sparingly soluble in water. Sparingly soluble means what? It will be not completely soluble, a bit of soluble, but highly soluble in hot water. So how it is obtained? It is obtained when you heat your borax. So you can see here borax, when you treat it with HCl or dilute H2SO4, it gives you orthoboric acid, NaCl plus orthoboric acid. So it is also obtained from mineral, that is columnite, by passing SO2 gas through a mixture of powdered mineral in boiling water. So this is the reaction. Okay. So what are the uses of orthoboric acid? So it is used as mild antiseptic for eye wash. Okay, it is also named as boric lotion. Okay, it is used as food preservative. Then it is used in preparation of enamels and glazes on this. Okay, so this is H3PO3. So H3PO3, it links up to give you such structures. Okay, so this is orthoboric acid structure. Next is diborane. Diborane is important this compound of borane. Okay, so this is the structure of diborane. You can see it is a dimer-like structure, right? So dimer B2H6. So B2H6 is nothing but diborane. So diborane, it is a simplest boron hydride. Okay, so how it is prepared by treating your boron trifluoride with lithium aluminum hydride. Okay, in ethylene, dialene ethylene. Okay, so it is just see here the reaction. So the reaction goes like this. So reaction is given. So go through the reaction. So this is the preparation of your diborane. So in laboratory, the diborane is prepared by oxidation of sodium borohydride with iodine. Okay, so this is the in laboratory you can prepare your diborane with this particular reaction, and in industry it is prepared by reaction of BF3, okay, boron trifluoride with sodium hydride. So this is the reaction of your, this is the reaction, how you prepare your diborane in industry. Okay, so these are the various preparations of your diborane. So what are the properties? So it is colorless, boiling point 180. Okay, it catches fire spontaneously when exposed to atmospheric air. It burns within oxygen. So it is the reaction is exothermic with release of a large amount of energy. So you can see the energy releases minus 1973 kilojoules per mole. Okay, so it readily hydrolyzed by water to form boric acid. So this is the reaction. So this is the structure of diborane. Okay, this is a structure of diborane. So it is, so what is a, you can see here, so it is a two-centered, okay, it is said to be a two-centered, okay, so it is two-centered bonds are there and three-centered bonds are there. So this is called as two-center. So with boron and hydrogen here, and boron, hydrogen, boron, this is three-centered. So it is called as banana bond. Okay, so three-centered electron pair. So this is three-centered electron pair bond. So this is three-centered. So between these three atoms, there are two electrons, and this is called as two-centered two electron. Okay, so this bond, this bond is called as banana bond. Okay, so this is the structure of diborane. So diborane, it is electron deficient. So it undergoes such, so it has 4 terminal pH bonds, okay, and in center it has 2 banana bonds. So this is the structure of diborane. So this is a, remember borozole, okay, borozole is nothing but it is an inorganic benzene. Okay, it is an inorganic benzene. The structure is like this. The structure of borazole is like this. So remember this, it is like a benzene, but alternatively you have boron and nitrogens. Okay, you have boron and nitrogen. So this is borozole. So borozole, it contains 3 double bonds and 6 pi electron system, which is similar to benzene. Okay, what is, if the question asked what is inorganic benzene, so it is borozole. Okay, it is borozole. So borozole is the inorganic benzene. It is similar to that of benzene. So this is the structure of boron. So based on this group 13, we'll solve some questions on group 13, then we'll go for the group 14. Yes. So borax bit test is not given by. Borax bit test is not given by. So here the answer is yes. The answer is C. Yes, Chandana, Damini, it's correct. It is C. Okay. So aluminum salts. So here cobalt salts, they produce blue color bits. So when you do borax bit test with cobalt, it gives you blue color bits. Then copper salts, they produce sky blue bits. Okay. Then your aluminum salts, they do not give color. It gives you a colorless bit. And nickel salt, they produce yellow brown bits. Okay, so borax bit test is nothing but it highlights you. So it is about the aluminum salt. So aluminum salt, they do not give you borax bit test. Okay, so rest all, they give you the test for borax bit. So we'll go for the next one. Which one is metaboric acid? Yes, which is the metaboric acid? Metaboric acid. Which is metaboric acid? So metaboric acid, what is the formula? Yes. So metaboric acid is nothing but it is a name of the family of inorganic compounds formed. Okay, how it is formed? By dehydration. So by dehydration of boric acid. So boric acid, you know, it is H3BO3. Okay, it undergoes dehydration to give you HBO2. So BO2. So the answer is HBO2 is metaboric acid. Yes, A is the correct answer. So most of you have answered it right. So it undergoes dehydration. Okay, it undergoes dehydration to give you HBO2. So boric acid, it undergoes dehydration to give you HBO2. HBO2 is your metaboric acid. So correct. We'll go for the next one. In diborane. So in diborane, what is the correct statement according to the structure? What it has? Yes, I'll write the structure of borane. Yes. So what it has? Yes. Yes, correct. So it has what? It has two bridged hydrogen, right? There are two bridged hydrogen and four terminal hydrogens are present. So it is, this is the correct answer. Yes, most of you have answered it right. So we'll go for the next one. So in diborane, banana bond is formed between. Yes, banana bond is formed between. So banana bond is formed between. So this is, so again, I'll write the structure. Yes. See here, when you're talking about such this, so this is said to be a banana bonds, right? So these are said to be banana bond. So banana bond is formed between three center two electrons. Okay, that is three. Okay, so it is what? 2 electrons are between 3 atoms, right? So it is what? It is A, right? A is the correct answer. Yes, good. So this is said to be, so when you are talking about banana bond, so banana bond is formed between 3 atoms and 2 electrons are there. And your this terminal atom, it is what? It is 2 centered, that is 2 atoms and 2 electrons are present. So 2 centered, 2 electrons, okay? And your banana bond is 3 centered, 2 electron. Understood? So we'll go for the next one. Boron trifluoride molecule has planar structure. Correct explanation for this is, so BF3, right? We had seen BF3, BF3. So this is BF3. Okay, so it has a planar structure. So what type of hybridization it is? How many sigma bonds are there? So there are how many sigma bonds? 3, right? 3 sigma bonds are there. Yes. So it is 3 sigma bonds are there. Okay, 3 sigma bonds are there. So out of that, so one will be S. So one will be S and another will be 2sp2. Okay, so it is BF3 is a sp2 hybridized. Okay, it is sp2 hybridized. Correct. Good. Okay, so I hope you have understood. So we'll go for the next one. Which of the following molecule has trigonal planar geometry? Yes, ammonia. So if we see ammonia structure, what is ammonia structure? It is pyramid, right? It has a pyramid structure. Ammonia, it is pyramid. So N like this, right? It has a pyramid, right? Trigonal pyramidal. Then your PCl3, PCl3 also it has a trigonal pyramidal. So this two are okay. Then IF3, it is also a trigonal pyramidal. IF3. Then BF3, it is a trigonal planar. So answer is B. Okay, it is B. B is the correct answer. Yes. So we'll go for the, I hope you have understood it. We'll go for the next one. Which of the following is not a protonic acid? Which of the following is not a protonic acid? Protonic acid means what? Protonic acid means what? It releases protons. Okay, it releases protons. When it is dissolved in water, it releases protons. So the answer is B. Yes, it is a boric acid. Acid is not a protonic acid. Okay. So boric acid, it is what? This is from H3BO3. Okay, it is from H3BO3. This is H3BO3. SO2, it is from H2SO3 minus. Then PO, it is H3PO4. Okay, orthoboric acid. Orthophosphoric acid. This is orthoboric acid. Then this is H2SO4. Right. So out of the 4, boric acid, when it is added to water, it is acting as a what? It is acting as a, okay, it is acting as a what? It is acting as a Lewis acid. Okay, while rest of the 3, it will happen when they are dissolved in water, they loses proton. Okay, so they act as what? They act as protic acid. They act as protic acid. Why they act as protic acid? Because when they are dissolved, the other 3 as acids, when they dissolved in water, they releases H plus ion. So they are called as protic acid. Okay, and your BO3, it acts as a Lewis acid. So this is a correct explanation. In diborane, the 2 HBH angles are nearly. So here, so the angle H okay. So remember the angle here it is 97 and this is 120. Okay, remember this. So it is, which is the answer? B, right? B is the answer. So remember diaborin is a very important topic. Okay, so diaborin is a very important topic. So most of the questions will be asked on that. So uh, such questions can be asked. So the angle is 97 and 120. Remember this. Okay, so we'll move for the next one. Which one of the following is not a metal? Which one of the following is not a metal? Which one is not a metal? Yes, Pallavi. Yes. So it is A, right? Boron. As we had discussed, boron is not a metal, right? What happens to metallic character as you go down the group? It goes on decreasing. Non-metallic character, it goes on decreasing, right? So boron is a non-metal, while the okay, as you go down the group, the metallic character it increases. So boron down the group, as atomic radius increases, the metallic character goes on increases. Hence, gallium, indium, thallium, they are the metals. Okay, and while boron is a non-metal. Okay, so we'll go for the next one. The stability of +1 oxidation state increases in the sequence. Yes, I had discussed about oxidation state. So can you tell me the stability of +1 oxidation state increases in the sequence? You have to tell the increasing this. It is D. Yes, Chandana, it is D. So how it is D? Yes. So on the okay, on the group due to what happens? So aluminium, right? Gallium, indium, thallium, right? So as you go down the group, okay, as you go down the group, what will happen? There will be increase in what? It will be increase in the okay, it will be increase in the inert pair effect tendency. Okay, it will be increase in the inert pair effect tendency to lose only one electron will increase. So as you go down, what will happen? The tendency to lose one electron will be more. So hence the order will be aluminum is less than gallium, is less than indium, is less than thallium. So you know, okay, boron and aluminum, it mostly forms what? +3. As you go down, gallium, indium, thallium, they form both +3 as well as +1. But more stably, they will be able to lose because of inert pair effect. It will be most able to lose only one electron. So this is the correct order. So it is D. Okay. This is the correct answer. So we'll go for the next. The most stable oxidation state exhibited by thallium is. Yes. So we had discussed it just now. What is this most stable oxidation state exhibited by thallium? Yes, it is +1, correct, right? +1. So as thallium, you know, as it lies down the bottom of the group, okay, down the group, what happens? It has maximum inert pair effect. So due to which it has only tendency to lose only one electron. Okay, thus it is very stable with oxidation state of +1. Okay, so due to inert pair effect. So next, boron shows single oxidation state due to the absence of why it shows only single oxidation state, that is +3, right? Why it shows only single oxidation state? What is the reason why it shows only one single oxidation state? Yes, Abhishek, yes, it is A. It is inert pair effect, right? So, electronic configuration of boron is 1s2, 2s2, 2p1. So, due to the pair, there is absence of inner d or f orbitals, right? So, as you go down, you can see there are presence of d and f orbitals. So, here you can see in boron, the electronic configuration is 1s2, 2s2, 2p1. So, there is absence of d and f orbitals. Okay, so it does not exhibit inert pair effect, and hence it loses all its 3 electrons. So hence it loses all its 3 electrons, and thus okay, from its outermost shell, and it can exhibit only +3 state. Okay, so this is the reason, due to the absence of inert pair effect. So borazole is known as, yes, what do you mean by borazole? What do you mean by borazole? What do you mean by borazole? Yes, it is inorganic benzene. Yes, Damini, it is right. It is inorganic benzene. Okay. B3H6N3. Okay, B3H6N3. So remember this, it resembles to your organic benzene. Okay, correct. So most of you are answering it right. So we'll go for the next one. So chemically borax is what is the name? Chemically borax is. Okay, the formula goes like this. Borax Na2B4O7.10H2O. Yes, can you tell me the name? Yes, Parvati, it is right. It is sodium tetraborate decahydrate. Okay, it is sodium tetraborate decahydrate. So this is the correct answer. Yes. So we'll go for the next one. Borax is prepared by treating colemanite with. Yes, we had seen this borax, how it is prepared by treating colemanite with. So it is Ca2B6O11. Okay, plus 4Na2CO3 plus H2O, giving you 3Na2B4O7 plus 4CaCO3 plus 2NaOH. So it is treated with Na2CO3. Okay, C. C is the correct answer. So borax is prepared by treating it with sodium carbonate. Okay, next. Yes. So now we'll go for group 14. So we'll see theory, some of the points behind group 14. So group 14, what is consists of group 14? So group 14, it is nothing but your carbon family, right? Carbon family. So it consists of carbon family. So here you can see carbon, silicon, germanium, tin, and lead. Okay, these are the elements of group 14. So these are the some of the elements of group 14. So carbon and silicon, they are non-metal. Germanium is a metalloid, and this lead and tin, these are your what metals. Okay, so carbon and silicon, these are non-metals. Germanium is metalloid, so it is acting both as metal and non-metal. So metalloid is nothing but it acts both as metal as well as non-metals. Then carbon, it is a 70th, okay, 17th most abundant element by weight in Earth's crust, and forms many compounds than any other elements except hydrogen. Okay, so this is the abundance. We are talking about abundance. So remember, your carbon and silicons are non-metal. Germanium is a metalloid. It acts both as metal as well as non-metal. While lead and your tin, it is your metal. So carbon, it has two stable isotopes. Okay, C12 and C13. Okay, so see the percentage of C12, it is 98.9%, and C13, it is 1.1%. Okay, So this is widely distributed in nature in free state as well as in combined state. So carbon has the third isotope also, that is C14, and it is radioactive and it is used for radiocarbon dating. Okay, so carbon, so it has mostly the three isotopes. So carbon 14, it is used for radioactive. Okay, it is used for radiocarbon dating. So in elemental form, it is available. So these are the allotropies of carbon. It is in the form of coal, graphite, and diamond. So these are the allotropies of your carbon. So carbon in elemental form, it is available in coal, graphite, and diamond. Okay, so you can see coal, graphite, diamond. Okay. Next, in combined form, it is available as metal carbonates, hydrocarbons, carbon dioxide gas. Okay, carbon is a versatile element in the world. Okay, so fats, carbohydrates, protein, vitamins, and fossil fuels such as petroleum, lignite are made up of carbon compounds. So you know carbon is essential components of all living organisms, right? So carbon compounds and carbon related okay, so these are all the fossil fuels, you know, fats, carbohydrates, protein, vitamins. So these are all essential constituents for living organisms. So next is silicon. So silicon is also the second most abundant element found in the Earth's crust. Okay, it is present in the form of silica and silicates. So it is the most important components of ceramics. Okay, ceramics, then your glasses and cements. Germanium, it occurs only in traces. It occurs in the form of, okay, germanium, it is existing in traces. Then tin occurs as cassiterite or tin stone. Okay, and lead as galena. So remember the this. Okay, these are some of the forms. So tin occurs as cassiterite and or tin stone, and lead as galena. Then pure germanium and silicon are used in making transistors and semiconductor devices. So these are the electronic configuration. You can see the what these are the different properties of, these are the different atomic and physical properties of group 14 elements. Okay. So what is the general electronic configuration? The general electronic configuration of carbon family, it is Ns2Np2. So the inner core of electronic configuration of element in this group differs. Okay. So hence carbon and silicon has inert gas core. Germanium and tin have inert gas core plus 10d electron. Okay. But your lead has inert gas core plus 10d electrons and 14 electrons. Okay, you can see the electronic configuration. So carbon and silicon, they do not have inert gas core. Okay, they do not have inert gas, so they have an inert gas core. Then here germanium, tin. So germanium, they have what, d, okay, 10d electrons. So they have a 10d electrons. The tin, they have d electrons. Lead have d electron as well as your f electrons. Okay, so the this is your general electronic configuration. So how it varies? So we are considering atomic ionization electronic okay. So atomic radii. So atomic radii of these elements, they regularly increase. So as you go down the group, what will happen to the atomic size? It goes on increases. Why? Because there is addition of new shells at each succeeding element. Okay. So as you go down the group, so there is addition of new shells. So because of the reason, atomic size of this element goes on increasing. So the increase in atomic radii from silicon onwards is, however, small. Why? The reason is again ineffective shielding of the valence electrons by intervening d and f orbitals. So because of the presence in d and f orbitals, so the atomic okay, there is sudden decrease in the atomic radii. Okay, because of the ineffective shielding of the valence electrons. So ionization enthalpy. So ionization enthalpy of group 14 element is slightly higher than that of the group 13 elements. Why? The reason is due to the increased nuclear charge. The influence of the inner gas core is visible. Okay. What happens to ionization enthalpy as you go down the group? It decreases. Okay, it decreases. Then electronegativity, due to the small size, the element of these groups are slightly more electronegative than the corresponding group 13 elements. So as you compare the electronegativity with group 13, so these are slightly smaller. So, you know, as you go across the period, what will happen to atomic size? It goes on decreases, right? So because of this reason, the electronegativity will be slightly more, okay, because of the small size as compared to group 13. So electronegativity decreases as you go down the group, okay. The electronegativity values for elements from silicon to lead are almost the same. Carbon with electronegativity of 2.5 is the most electronegative element of the group 14. So carbon, as it is the small in size and it is the first element, so it has a electronegative value of 2.5. So what about the oxidation state? Okay, when you are talking about oxidation state, so the group 14 elements have 4 electrons in the outermost shell. All the elements show an oxidation state of group 4. Okay, so plus 4. So you can see carbon, it shows plus 4 or minus 4. Silicon shows plus 4. Germanium, tin and lead, it shows plus 4 and plus 2. So however, as we move down the group from carbon to lead, the stability of plus 4 oxidation state decreases and that of plus 2 oxidation state increases due to the inert pair effect. Inert pair effect, why? They're due to the presence of D and F orbitals, okay, F electrons in the orbitals, and okay, because of the intervening of D and F electrons in the orbitals, okay. So plus the stability of plus 4 oxidation state decreases and plus 2 oxidation state increases. So physical properties, all the carbon group 14 elements are solids. Carbon and silicons are non-metal. Germanium is a metalloid, while tin and lead are soft metals. Okay. The melting point and boiling point of group 14 elements are higher than those of group 13. So this is due to strong interacting binding force in their solids as well as in liquid state. Down the group, there is regular decrease in the melting and boiling point as the size of the atoms increases and interatomic forces of attraction decreases. Okay, hence silicon is hard while the lead is soft in nature. So as you go down the group, what will happen to melting point and boiling point? It goes on decreases. Why? Because there is size increase. Okay, and the what happens to interatomic forces of attraction also decreases because there is increase in the size. The interatomic forces of attraction also decreases. So because of this reason, silicon is hard, while lead, okay, lead, it is soft metal. So we'll see some of the reactions. So the elements of carbon 14. So here you can see group 14 form two types of oxide. They form monoxide as well as dioxides. So of all elements of group 14 except silicon, they form monoxide. Dioxide, so CO2. CO2, it exists as a linear monomeric compound. So E. So E is here any element from this particular group 14. So when it reacts with O2 molecule and heat, it gives you a dioxide. So they give you dioxide. So reactivity with water. So carbon, silicon and germanium are not affected by water. Tin, they decompose steam to form dioxide and hydrogen gas. So you can see the reaction SN, that is tin plus water. When you heat, it decomposes to give dioxide. Tin dioxide plus H2 gas is liberated. So lead is also unaffected by water. So lead always form a protective oxide film on the surface. Okay. So lead also always it forms a protective oxide film on the surface, right? So when you react it with halogens, so two types of halogens are formed. One is tetrahalides and dihalides. So the tetrahalides are covalent in nature. Their thermal stability, what happens to thermal stability? As you go down the group, it decreases. Okay. And tetrahalides of group 14, except that of carbon, are readily hydrolyzed. So this is a reaction. Silicon tetrachloride plus 4 water molecule gives you silicon hydroxide plus 4 HCl. So in carbon, there are no vacant d orbitals, hence it cannot increase its valency beyond 4. So carbon at the most it can form +4 oxidation state or -4 oxidation state. So therefore tetrahalides of carbons are not hydrolyzed. So the stability of dihalides of group 14 increases as we descend the group. So as you go down the group, the stability of dihalide goes on increasing. So how is the behavior of carbon different from the other elements? Okay. So first element of other group, that is carbon, differs from the rest of the members of its group. It is due to the why it is behaving anomalous behavior, because of the small size, higher electronegativity, higher ionization enthalpy, and unavailability of d orbital. So why the first element, it shows different behavior from rest of the elements of the group because of its small size, due to its high electronegativity, high ionization enthalpy, and unavailability of d orbitals. So in a carbon, only s and p orbitals are available for bonding. Therefore, it can accommodate only 4 pairs of electrons around it. So it would limit the maximum covalency to 4, whereas other members can expand their covalency due to the presence of d orbitals. So at the most, the electrons covalency found by carbon is 4, while the other members of the group, they can expand their covalency, because as you go down the group, there is a presence of d orbitals. So the covalency can be expanded. So catenation, so carbon has the most unique property of called as catenation. Catenation is nothing but these carbon atoms, they have a tendency, okay, they link with one another through covalent bonds to form rings, or they form a chains like structure. So this property is nothing but it is called as catenation. Why this catenation? It is due to the presence of the cis bonds. Okay, these cis bonds, they are very strong. So catenation, it is a unique property shown by carbon. It has a tendency to link with one another, okay, through covalent bond. So down the group, the size increases and electronegativity decreases. So the tendency to show the catenation decreases. So the order of catenation is carbon is greater than silicon, is greater than germanium, is greater than tin. Okay. Catenation, lead does not show catenation. Okay, carbon also has a unique property to form pi multiple bonds with itself or with other atoms. So it can form C double bond C, C double bond O, C double bond S, C double bond N, right? So these are the, so it forms different, it has the ability to form multiple bonds. So due to the property of catenation and pi bond formation, carbon is able to show allotropic forms. Okay. So which are the different allotropes of carbon? What do you mean by allotropy? Okay, what do you mean by allotropy? Allotropes are different physical forms of the same element which have same chemical properties but different physical properties. Okay, so these are said to be allotropic form. Okay, so they are having different physical properties, and they have different physical forms of the same element, but they have same chemical properties. Okay, so these are allotropes. So which are the different allotropes? Diamond, graphite, fullerene. Okay, then amorphous carbon and carbon nanotube. Okay, so these are the allotropes of carbon. So the 3 allotropes of carbon, so the diamond, graphite, and Buckminster fullerene. So, okay. So we'll discuss about this allotropes in the next class. So along with the allotropic forms, and we'll solve some of the questions on group 14. So we'll see this in the next class. I hope today's section, okay, group 13 is clear, and whatever the synopsis I have done for group 14 so far, it is clear, right? So we'll stop for the day today, okay, and we'll continue in the next class. Thank you. Have a nice day.